Okay, just a moment. So let's start with some reminder. So our topic is the quantum determinant. Recall the notation. Notation is Q det T of U, or I will use the more compact notation, D of U. It is, as usual, it's a formal power series. Which belongs to our Yangian extended by formal power series. And the definition is as follows. Definition of quantum determinant, recall it, U is the sum over all permutations, the sign of the permutation, and with shifts. Of the formal parameters. And at the last step, we get this one. Let me recall also that by definition, a formal power series again. And these are generators. These are generators of a Yangian. Of a Yangian. And the subject to defining relations. Generators. Our object subject to an infinite system of defining relations in the compact form. It can be written in this way with the help of the Young matrix. And P is a matrix and operator. And V is my notation for the coordinate complex space. And okay, maybe I call also the notation. This is the matrix with the entries in my Yangian with formal parameters, and also this is the same as my algebra and tensored with and V. And the theorem I want to prove and started to prove in the previous lectures says that d of u is in the center. More precisely, this means that all these coefficients, which are elements of my algebra, are actually in the center of a Yangian center. So this is the claim. This is the claim. And today I want to complete the proof. Let me recall the notation. The notation, I will use it. I will write it in a slightly different way. This is a double product with respect to the first index I, next the index j, which is greater than I, so it starts from I plus 1 until m. And here we have the R matrix with the formal parameter. And the notation is as follows, which means that we write all the factors from right to left, not from left to right as usual. And I recall also that this is the same. I simply rewrite this, same notation. But let me also simply write it by recalling what is the R matrix. So this object is the permutation of the tensor factors number I and number j. In the all this picture is developed all this leaves where in complicated object Yangian formal parameters tensored with the space multiple tensor space. And this is the permutations of factors here. Okay. Is it clear? Some questions maybe? Please ask. It's okay. Let me recall the results from the previous lecture. The fundamental identity, fundamental relation. It looks as follows, that we have and on the right, we have the same product by in the reverse order. So this is the product just defined, this one. And this is my shorthand notation. So this is very important. And the second result from the previous lecture is the factorization of the anti-symmetrizer. Okay. So I recall what is the anti-symmetrizer. It is an element of a group algebra of a symmetric group with m letters. The definition is quite simple. It is the alternating sum of the group elements of the permutations. This one. And the result is as follows. I recall it. it is equal to quite a similar product from right to left as above. And here I put this one. And this is transposition, with transposition. These two letters, I assume that I and J are distinct, which is clear from this. So let's compare. Let's compare this and this. Okay. What I need next? I need next, I want to define the action, the natural action R of our symmetry group on this tensor space by permutations. More explicitly, so assume that I will use Greek characters alpha and beta as a multi-indices. So reform so this is a M tuple of numbers. Each of these numbers is one of these positive numbers, natural numbers. And so we have that alpha, these multi-indices are natural parameters. These are parameters of basis vectors of our space, our tensor space. So what I mean, this is I assume that, and this is the basis, standard basis. Okay. And now the action of a symmetry group, given a permutation, the corresponding operator on the tensor space is defined as follows. It's a little bit difficult maybe to imagine, but actually the group acts not on the coordinates, which would be absurd because the coordinates are here. The group acts on the positions of these coordinates. And a little argument show that we have to invert the permutation to get the left action, which is maybe it's better to understand this because the space is the space of the mappings to this space. And from this picture, it becomes clear that we have to put this to get a left action by change of argument. We have to replace we have to put -1. And the corollary. So after all this little discussion, the corollary of this result is as follows. Assume that these differences are equal to j-1, which means that u sub I is equal to sum u minus I plus 1. So this is exactly what happens in the definition on the quantum determinants with shifts. So assuming this, we have that our product of the R matrices is nothing else than the image of the antisymmetrizer in the tensor space. Sometimes I will, sometimes we will write simply AM instead of the operator, which is a little bit incorrect, because if the symmetric group is large and the dimension n is small, then this action is not faithful. So, but sometimes it's more convenient to drop this letter to make the formula more compact. Okay. So what we have this very important for our purpose relation. But this happens only, of course, this happens only under this assumption. Okay, is it clear? Maybe some questions at this moment. Let me stop for a moment. Is it clear? Okay. Now, I want to relate the quantum determinant to this discussion, and this is done via this lemma. Which says the follows. Take this product, we will take m equal to n, and take our antisymmetrizer and our product as usually. I'm sorry, this mistake. And the claim is that it's equal to the same operators in times our quantum determinant. How to understand this? So the proof. First, maybe it's convenient to introduce some little notation. A and tilde is the same antisymmetrizer, but with a normalization. This normalization says us that this element is an idempotent. Idempotent meaning that which is quite easy to see. Moreover, the corresponding operator, which is normalization of this, it is a one-dimensional projection operator. Projecting operator on our tensor space. I think it's clear because it projects onto the maximal exterior power, which is viewed here as a subspace, not a quotient space, by a subspace. Or maybe it's better to say that it's the projection onto the one-dimensional subspace, which is spanned by the result of anti-symmetrization of a natural vector with numbers 1, 2, 3, and so on. So more detail, it's the same as take this alternating the sum. It is a distinguished vector in our tensor space, and this operator is one-dimensional. And let's continue. So we know that we have I want to slightly rewrite this claim, this one with m equal to n, and I want to rewrite it by normalizing this operator. So what we have by corollary, simply, yes, this is corollary, indeed. Sorry. Corollary. We have and here we can replace by this projection operators, and it follows that the right-hand side is invariant under multiplication on the right by this projection, because we can put here normalized operator, but it is a projection, so it is invariant under multiplication by itself, and so the same holds for the left-hand side. This is a key argument. So the same holds for the left-hand side. Left-hand side. And it follows that the left-hand side has the form times something, which is an element of our algebra. Let's rewrite this because I want to use the non-normalized. Which is the same. Okay. Let's denote this. But actually it is the quantum determinant. So I want to prove this. But what we have? Now we have the relation. I rewrite again, maybe in more detailed way. We know that it's equal to some element times, and let me emphasize again what is non-trivial. What is non-trivial? On the left-hand side, this operator sits on the left, but actually it appears on the right. In general, if you put some factors here, we cannot claim that this operator can be put on the right. A little argument shows that because of the non-commutativity of our algebra, it's impossible. Maybe I will explain this in more detail a bit later. So we have this relation. And what next? We want to compute. We want to extract this object from this relation and show it coincides with the quantum determinant. So this is the idea. Some questions maybe, is it clear? Not? Looks clear, okay. Some questions? No? Okay. So my goal is now to show that which is defined by this relation coincides with the quantum determinant. How to do this? The idea is as follows. Idea: apply both sides. We regard this at this moment as operators on our tensor space with some coefficients which are elements of our algebra. So we can apply this to some vector from our tensor space. So we apply it to the most natural vector of sides 2. Tensor space. And look at the coefficients of the same vector. And this coefficient is some element of our algebra. So this gives us on the right-hand side, here, if we apply this, what happens? First, we apply this operator to this vector, And it gives us the alternating sum, which is obtained by permuting these factors. So the coefficients is one. So we get on the right-hand side, we get exactly this. Is it clear or not? So we do this just as these elements be scalars. For us, they are scalars. The fact that these scalars live not in the complex number, but in some non-commutative algebra does not matter. All is okay. So these are simply coefficients. But now let's compute what happens on the left-hand side. To compute the left-hand side being applied to this vector, what we get. So let's write what we get on the left-hand side. So we have this operator and times again this object and applied to this vector, but write in more detail these. And what are our TI? We write this as follows. Maybe it's not a good notation. The problem of notation is very serious in this story. Let me write just maybe I will write sum of multi-indices which parameterize the basis vectors. So we have n. And next we have to multiply by and finally we have our this is the left-hand side. And what next? What next is we want and we can to move this operator here. Is it clear to us why is it possible? Because these are simply coefficients. The fact that they are non-commutative play no role. These elements, this operator want only to do something with this object and not this one. So these are simply coefficients. And what happens now? So this is the same as the sum. And again, I write and okay, let me write in more detail. I'm sorry for maybe too detailed writing, by I would like to make all the things clear. So what happens now? Look at this expression. What happens? What happens? The contribution of this term is non-zero only if these indices, the beta indices, are 1 to n by the very definition, because this matrix units acts on this vector and so on. So you can assume that this multi-index is exactly. Then what we get that the same expression is and we apply this permutation operator to the result of application. Sorry, there is no beta here already. Beta disappears from the story, and we have and what we get. You have to look at this expression, the result of antisymmetrization of this tensor. So we know what happens. There appears the second sum of the permutations. So we have sum over alphas and the sum over the permutations. We get again this expression. And I recall what happens now. We have to write the result of application, and I forgot the sign of a permutation. But we want what we want. We want the coefficient of and this coefficient, this. I'm sorry. Nobody corrected me. This should be, because beta is equal to 1 to 3n. And we want this coefficient appears for what is this? This is the basis. This is this vector. So what you get? I think it's clear. The result, maybe I made some little problem, little error, but this maybe should be equal to 1, and this should be equal to n. So the result, maybe I will skip, but the result, the correct result is what we want. So the sum of alpha disappears because for S fixed, the corresponding alpha is defined from the condition that this tensor should be equal to this one. Okay, so we get, finally we get what we want, the sum and this is, by the very definition, is the quantum determinant. So the lemma is proved, and I want again to ask for possible remarks, questions. So please ask if something is not completely clear. Okay. No questions. So maybe I would like to discuss a little bit. So I recall what we have proved. So please look at this relation, the result of our computation. What does it mean? It is an analog of the well-known fact in the commutative case. If you want to compute the determinant of the operator, you can do in the following way. We take the exterior power of our operator. So you have, let me write this. Remark. Remark commutative case. So assume X is an n by n matrix, complex matrix, and we want to compute the determinant. How to do this in some, one can say, invariant terms? We take the exterior power, the complete exterior power, which is the direct sum. This is an operator on the Grassmann algebra generated by our space. Product. And our operator, the action of our operator is consistent with this grading, and in particular, it acts on the maximal, on the highest component, which corresponds to little n equal to capital N, which is a one-dimensional space. So on this one-dimensional space, on the higher exterior product, it acts as a scalar. And this scalar is our determinant. So this is a well-known fact. And what I proved is some non-commutative analog of this claim in a special situation of a matrix with non-commutative entries subject to some non-trivial and very special defining relations. So this is some analog of this well-known fact from linear algebra. But why such a complicated interpretation? Because it is well adapted to the form of the RTT relation, which is the most convenient form to write the defining relations. So this is an analog of this. What is the difficulty? The difficulty arises from the fact that the picture is non-commutative. If our X is a matrix with non-commutative entry, some algebra which is not necessarily commutative, that the definition of a determinant is unclear. So we have at least two versions, the column determinant and the row determinant. And in general, they are different expressions. And to make them the same, in our case of a Yangian, we need to include in the definition these shifts. This is very important, these shifts. And the origin of the shifts is the factorization of the antisymmetrizer. So this is, I try to make it a little bit clearer. Now I want to continue the proof. So I recall my goal. My goal is to prove the quantum determinant is in the center. And how to prove this? Actually, one can prove more. One can prove some analog of this claim for quantum minors. So my goal now is to introduce quantum minors. Quantum minors. In the commutative case, what are minors? What are minors? In this picture, the minors are matrix elements of these big operators, which acts on this space. Taking some component, in general, the homogeneous components, the homogeneous components are not one-dimensional, only the first and the, I'm sorry. This is stupid. Only two components are one-dimensional, but zero is not interesting because the action is trivial. But all the remaining components are multidimensional, and we have natural basis in these components. These are the products, the exterior products of our basis elements, and the corresponding matrix elements are nothing else than the minors. And we want to do something similar in our non-commutative situation. So how to do this? So assume that we have some non-commutative algebra in this situation. Let me introduce some notation for the tensor space. For tensor space, I need some notation. So, as before, I assume that beta are multi-indices. And notation. Given a pair of the two multi-indices, alpha and beta, I will denote. This is by definition the following object. This is an operator. So this is simplification. And they are a basis. Our not on the tensor space, I'm sorry, but on the space of operators. One could say that these are analogs of the matrix units. One could write as follows, but this is maybe a little bit confusing. So I will write in this way. So alpha is the multi-index corresponding to rows, and beta corresponds to columns, according to this notation. So assume, so I want to continue a little discussion of notation. So assume that X is something like this, some non-commutative algebra and tensor with this space. Now I can expand this with respect to this basis. I do this just if this algebra be the field of complex numbers. So I can write that X can be represented as the sum of the pairs of multi-indices, some coefficients denoted as follows, and our matrix units. But of course, these are not numeric coefficients. These are elements of my non-commutative algebra. So this is my notation. This is my notation. And this is the definition of these quantities. Some little properties. Properties of so assume that we have such a relation. My normalized antisymmetrizer acting on the tensor space. So this is a projection operator. In general, not one-dimensional, but some projection operators. So assume that our object viewed as an operator on the tensor space with non-commutative coefficients, but this does not matter. Assume it is invariant on the left. And this implies that the coefficients are antisymmetric, skew-symmetric, one could say, antisymmetric, with respect to the action of our permutation group on alpha, on the row indices. When we permute these indices according to the action of our symmetric group, we get the sign of a permutation. And likewise, if X is equal, I'm sorry, this implies the same for the action on the column index, multi-index method. Is it clear or not? Please ask. Okay. Okay. Now we apply these remarks to our particular case. We put X being equal to our operator which is an element algebra. This is our algebra A, and times endomorphisms of the tensor space. Now, from this definition, we can produce some quantities which becomes elements of and denote them by T alpha beta of U. So this is the definition. This is the definition of these quantities. Is it clear? So we have two multi-indices, at this moment arbitrary. And let's call them quantum minors. So the definition the quantities defined by these are called quantum minors of our operators of order M. But at this moment, it's formally they are defined for any M. Formally at this moment, maybe. But what we have, we can apply our properties 1 and 2. Are applicable to our X, Y it is. So look at this expression. This is our definition. The left invariance is evident because of the presence of this term. But we also have another expression for the same object in which this operator appears on the right. So we get the right, the invariance on the right. So we can apply, so our X satisfies both this, which is evident, and also this condition, which is not evident, but it follows from our previous discussion, our previous result. All these stories developed in my previous lecture. So we can apply this. And applying this, we get that quantum minors are antisymmetric. Antisymmetric in alpha and in beta. And this also means that the alpha beta of u is equal to 0 in case of possible repetitions. Repetitions in alpha or in beta. If some coordinates, some two coordinates in alpha are the same, then the result should be 0. And in particular, is if m is greater than n, then always we have repetitions, and so we have 0. So the minors are actually defined for m, which does not exceed n. Is it clear? Okay.
It's all clear, yes.
Okay. So we have, and this is important. Let me start some next argument, but we have lemma. I want to...
Yes, то есть вот в конкретных совсем терминах вот эти квантовые миноры — это такие же, ну вот буквально квантовые определители минора. Это правильно? Ну просто вот пишем такую же сумму, как в обычном...
Ну да, но с той только разницей, что у нас эти строчки и столбцы, они у нас разные.
Да, ну да.
Да, с этой поправкой, да, именно так, да, совершенно верно, конечно. Формула совершенно того же типа. Я вот сейчас просто это и напишу на самом деле. This lemma is as follows. The claim is that is just as above. Let me skip your proof. It's easy. The same idea as I used for the quantum determinant. So we have this. And the corollary of this formula, that we get that in the particular case, we get the quantum determinant. This is evident from the formula. But now I want to state the result which extends the theorem about the quantum determinant. More general than about its set as follows. So assume that as before, alpha and beta are multi-indices. And assume that K and L are also some indices, not multi-indices, but simply numbers. And then, if K is contained in alpha, meaning that it's equal to one of the coordinates, and L is contained in beta, then this object generating series for the generators indexed by K and L commutes with the quantum minors. So this is a truly remarkable fact. Let's stop for a moment and discuss this. What is the claim? So we have some big matrix. We choose some collection of rows and columns. We take the corresponding minors. And if K and L are contained inside, one can say that this pair is contained inside this minor. Then a miracle appears, it commutes with the minor. This is more general. This is more general because this implies the theorem about du follows at once, because in this case we simply take this quantum minors, which is our quantum determinant. And in this situation, K and L are automatically contained here. So they commute. And this means that the quantum determinants is in the center because it commutes with any object like this for any formal parameters which is independent of U. So all the coefficients which are these generators commute with a quantum determinant. So I want to prove this more general result because it looks better. So let me give maybe, I will skip some details because the proof is a little bit tricky. So it's difficult to memorize, but I would like to demonstrate some ideas. So the proof goes as follows. So assume for a moment that K, L are arbitrary. So drop our assumption that they are contained inside. And I want to prove some little bit complicated formula, which says the following. Take the commutator with the quantum minor and we claim that it's equal to the following. I will write and then I will explain what happens. here I have a problem. How to write this? Maybe I will write as follows. I will explain in a moment what I have in mind. No. So what I mean here, E is obtained from alpha by replacing this component by k. So we interchange given I here, given I, we previously had here k, and we look at the component number I, which is this one, and we put instead k. And here, instead of k, we put this component. So we interchange we swap k and alpha. And likewise, in the second sum, given j, we do the same in the column multi-index.
То есть вот если альфа и бета – это один индекс, это просто соотношение Янгиана, да?
Да, 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 это его обобщение. Да, именно так. Именно так. Это такое обобщение. Можно было бы we could put it here, but it is the same. Exactly, you are right. So let me denote maybe this. And what next? How to prove this? So first of all, I would like to show that this claim implies our result. Mark. This implies the theorem. Why? But look what happens. So assume now, indeed, assume now K is contained in alpha and L is contained in beta. So what we have that K is equal to some alpha C P, L is equal to some coordinate say Q. Okay? But then on the right hand side, recall that these quantum minors, some tensors, are skew symmetric, anti-symmetric. So this result, this object vanishes unless I is equal to P. This P. Because otherwise we have repetition. Okay. And likewise here, this object vanishes unless J is equal to Q. So actually, we have only two summands here and not 2 times M. So the right-hand side. So in this situation, the right-hand side reduces to what? But it reduces simply, it reduces to T. The same commutator, which is on the left. So what we get? We get with this commutator is equal to the same expression under in our situation times this factor, but this only is possible if it's equal to 0. So this is the result we want, but we need to prove this formula. Okay, is it clear? Some trick. I think ingenious trick how to guess it, how to arrive to it, I don't know. In my opinion, it's a trick. So this implies the result, so but we need to prove. So we prove. Proof of the formula. So we have to work. We have to work with our fundamental identity. So we consider m+1 indices now. We add one more copy of our space V. So we are dealing with a tensor space with m+1 factors. And let's write our fundamental relation in this form. This is the same as one could. This is the same object. And put here and the same story begins. On the right-hand side, we have the same product in the reverse order. Let me write this first. And the same object. So this is step 1. Step 2 is to observe that this complicated construction can be written as follows. It can be written as our good object, which corresponds to, which corresponds to this tuple of indices because we have the good shifts here, and times some extra product. Some extra product, which is, what is this extra product? V minus U. And here we have R and V minus U plus 1 and so on. And here we have V minus U plus M minus 1. I think it's correct. But next, I have to use some trick from the previous lecture. A trick from the previous lecture, the computation, the factorization, which is used in the factorization of antisymmetrizer, almost the same, only a little modification is needed, shows that this quantity, this extra quantity, is actually equal to something much more simple. It's actually equal to these are permutations of the tensor factors. The fact that we have here not 1, 2, 3, and this number also increasing by 1. But we have this additional number. V does not matter. Because of this, it appears here. And that's all. Let me skip this, but it's true. So we can rewrite our relation. We can rewrite our relation in the following form. Let me write as follows. This depends on U. And this is the same as writing the same and again all this all these terms. Okay, let's rearrange all this. This can be written as follows. This is formally equivalent to what? I want to extract, to open the brackets simply. So we have on the left, and it is equal to what? Minus something similar. Okay. And what
Сейчас в левой части справа должен быть еще один R, да?
Да, вы правы. Да, спасибо. Значит, что теперь? What now? A little game is as follows. We remark that this object commutes with this and can be moved here. Can be moved. Can be moved. And likewise, this object also can be moved. Can be moved. And now one can write the stories as follows. So the right-hand side can be written as follows. And let me write this as x of u. I mean that okay, just a moment, sorry. Minus x of u and what is x of u? Here x of u is which is the same as is the same operator. after this move, this term together with this is equal to this term together with this factor. This is the same. So what we have this. And I claim that we get exactly what we want. We get exactly what we want because look at our claim. Our claim, this one. Okay. The left-hand side of our relation gives exactly this. We have this factor. Okay. And this swapping, this transposition, and the sum comes from the action of some permutations here, say number I, on this term. Because when we multiply this tensor, one can say, by some operator, say, this amounts to some switching, some swapping of indices. And this swapping is exactly what happens here. In the first sum, we get this transposition, and in the second sum, we get this one. So the formula is proved using this computation. So I'm sorry, maybe I'm late. But I hope that at least I gave the idea of this computation. And you can look at the book of Molev, where the same argument is presented. But the book is condensed, so I tried to represent it in some more detailed form with some comments, which I hope can help you to understand the computation, the ideas behind this computation. So let me stop at this moment. I will switch off